Hi, I'm Max Hopkins. I'll be talking about hypercontractivity and small set expansion on high-dimensional expanders based on joint work with Mitali Bafna, Tali Kaufman, and Shachar. Okay, I want to start off with some motivation and sort of the broader story of where we're headed with this line of research. And that starts with a story about expansion on graphs. So in particular, we study a fundamental combinatorial property of graphs called edge expansion. So given a graph G, a vertex set V, and edge set E, the edge expansion of a subset of vertices S is just a fraction of edges that leave that subset, that expand outwards. And typically a graph G is called an expander graph, essentially if it's all of its subsets, maybe up to complement, have good expansion. But, this value is large, many of the edges expand outwards. And these graphs, which are usually thought of as sort of sparse, robustly connected graphs, are extremely useful throughout theoretical computer science. They're sort of ubiquitous tools throughout complexity theory, algorithms, coding theory, even in other areas like networks. These are really useful objects. So they're sort of very well studied and fairly well understood at this point. But sort of the story doesn't, end here. It really just starts because many graphs of interest that we care about sort of aren't expander graphs, right? Structured objects like the Hypercube, for instance. But it turns out that on these objects, it can still be really useful to understand sort of the finer grained structure of expansion. Which sets are expanding? What are the obstructions to expansion? And as far as I know, sort of this was first studied in Boolean function analysis by Konkoli and Lunial on the Hypercube graph. And they proved something called the KKL theorem, which is now a very famous characterization of non-expanding sets on the Hypercube. And they also proved a sort of a very strong characterization of expansion on what are called the noisy hypercube graphs, which is sort of flipping each bit with some probability or something like this. And they showed that on these objects they have this very strong property that small sets expand near perfectly, meaning that sort of almost all edges leave the set. This is sort of a stronger regime of expansion than is typically studied sort of in what I introduced in the first slide. And these results at this point are sort of, considered revolutionary in the field of Boolean function analysis and have become, standard techniques in hardness of approximation and lots of other areas. So these are very also sort of traditionally useful tools. So what have we been doing since then? Well, recently there's been a lot of interest in sort of understanding this type of behavior beyond the Hypercube, right? Beyond this original object that was studied. And this includes graphs on sort of general product spaces, on slices of the Hypercube, on vector space structures like the Grossman, on algebraic structures like the symmetric group. And these sort of extended regimes all seem to satisfy the same sort of behavior. They're not small set expanders like the noisy Hypercube graph, but they do expand outside of some small number of canonical local obstructions. I'll say sort of exactly what these are in just a minute. But in other words, sort of if you have a set that is global or pseudo-random in some sense, that sort of avoids local obstructions, then you recover this type of expansion characterization. These sets expand almost perfectly. Okay, and why would you care about this? Well, I said that sort of the KKL theorem and analogous results in the Hypercube have had a lot of applications in hardness of approximation. And the new interest in these sort of extended regimes is the same. It's largely driven towards understanding structure that seems to be very important for the unique games conjecture. It's probably the most important open problem in hardness of approximation. It's actually been known for a long time that small set expansion is sort of inherently connected to the UGC. And more recently, it was learned that sort of further extended domains like the Grossman are also extremely important. In particular, it turns out that the key to resolving what's called the 2-to-2 games conjecture, which was this huge breakthrough towards the UGC, it's sort of halfway solved to the unique games conjecture, turned out to boil down to essentially understanding non-expanding sets on the Grossman graph, sort of on one of these extended domains that people have looked at. So sort of understanding these extended domains seems to be, very important for hardness of approximation. And okay, so what is the sort of the tool set that is typically used to prove these results? Well, basically all of these results are proved through a very powerful inequality in Boolean function analysis called hypercontractivity. Informally, you should think of hypercontractivity basically as saying that low degree functions or low degree parts of a function are nice in some sense. And I'll formalize this in just a second. And it sort of turns out that maybe morally and up to fudging parameters, hypercontractivity and this type of small set expansion, characterization or behavior are basically equivalent. You can sort of move between the two of them, only fudging things a little bit. Okay, so slightly more formally, To talk about hypercontractivity, we first have to talk about sort of standard Fourier analysis. So let's say that f is a function on the hypercube. It sort of standardly can be broken down into its Fourier basis, or here we'll use a coarser decomposition, just breaking it into sort of Fourier levels. So what I mean by this is that f can be broken into sort of a contribution from each level 0 through n, each sort of degree, where fi is sort of corresponding to the degree I contribution to f. And on the hypercube does literally correspond to some degree I, sum of degree I monomials, a degree I polynomial. And this is sort of a standard Fourier analysis. And hypercontractivity, or here I'll be referring to something called the Bonomi lemma, a very basic form of hypercontractivity, basically states that for reasonably small I, these degree I portions of f, these fi, are smooth in some sense. In particular, their 4 norm is upper bounded by 2 to the O of I times their 2 norm. And this basically means they're smooth because if the function were sort of spiky or weirdly concentrated, when you increase the Q norm, as you increase Q right here from 2 to 4, the function would spike up drastically. So this inequality is basically a smoothness statement, a niceness statement about Fi. And it's not too hard to show this sort of forward direction that the Bonomi lemma implies small set expansion. And I'll give you sort of the 2-word version of this proof. It's basically taking a sparse function and you apply Holder inequality, and then you use this classical fact that sort of these Fourier levels turn out to be the eigenvectors of sort of associated Cayley graphs, like the noisy hypercube graph or hypercube graph on -1, 1 to the n. And these are sort of standard results in spectral graph theory. They're worth looking into if you haven't seen them before, but we don't have time to go through them in the talk. Okay, but it's sort of enough to understand hypercontractivity. And unfortunately, sort of, it's not too hard to see that as soon as you move beyond the hypercube, this sort of Bonomi lemma and small set expansion start to break down pretty significantly. The classical example of this is just the p-bias cube, where p is thought of as being something quite small, like much less than 1 over n. The p-bias cube is just the distribution over the cube where each bit is 1 with probability p independently. And it turns out that in this case, there are sort of natural local obstructions to small set expansion, basically in the form of dictators or more generally subcubes. So to see this, let's consider the set S, which is just all of the binary strings which have 1 as their first coordinate, right? So this is the dictator on coordinate 1. And because we're in the p-bias distribution, the density of this set is really small, right? The probability that the first coordinate is 1 is p. So this is a set of measure p, which we're thinking of as quite small. But let's kind of directly look at the expansion of this set with respect to, say, t1/2, which is the walk that resamples each coordinate with probability 1/2. So with probability 1/2, you leave the coordinate as is. Otherwise, you resample it with respect to the conditional distribution. So the Bonomi lemma, sort of the full strength Bonomi lemma, as we said in the last slide, would predict that because this set is small density, it would be near perfectly expanded. It would have expansion sort of 1 minus little o of 1. But it's not hard to see that the expansion is actually much worse than this, right? In particular, when do we sort of leave this set? This is another way to view expansion, the probability that you leave the set S. Well, we only leave if we resample x1, right? We can't leave otherwise because it's totally decided by coordinate 1. And the probability that we resample x1 is at most, is exactly a half. So the expansion in this case is at most a half, which is much worse than 1 minus the low of 1. So we can sort of see that immediately we don't have small set expansion, and in particular, then don't have sort of full strength Bonomi lemma. But what many of these sort of recent works on extended domains showed was that this is actually the only obstruction. Sort of as long as you avoid these dictators or subcubes, you actually do have Bonomi lemma. You do have expansion, and in particular, they define these notions of pseudorandom functions that basically avoid subcubes, and you prove that hypercontractivity and the Bonomi lemma hold for these functions. And this is sort of how you get all of these extended domain results. They all have this flavor. So, okay, these hypercontractivity theorems, I mean, they clearly have a lot of similarities, right? They all basically are talking about these local types of structures. They all go through these local versions of the Bonomi lemma. But the proofs of these results are, it turns out, sort of often very involved and very tailored to the specific application, whether it's the Grossman or the hypercube or the complete hypergraph. They're all sort of very, very different. But the behavior is so similar that it really suggests that, there's something more going on here. It raises this natural question of whether there's really some sort of underlying unifying theory. Is there some sort of underlying mathematical structure that really explains, this behavior on sort of all of these, disparate extended domains, like the p-bias cube or symmetric group or slices and things like this. And what I want to talk about today for the rest of the talk is basically a candidate framework for this unifying theory, something known as high-dimensional expansion. So broadly speaking, I'll be a little bit more formal about this in a couple minutes. HDX are like a generalization of expansion in graphs to hypergraphs to high-dimensional objects. And in the last 5 years in computer science, they've seen sort of an amazing number of breakthroughs in a couple of areas, especially in approximate sampling, recently in coding theory with LTCs and QLDPC codes. So these are already sort of very useful and well-studied objects in the last 4 or 5 years. And let me sort of, before giving you the version of our main result, let me give you sort of a few reasons to believe why HDX might be a good framework to view hypercontractivity through and small set expansion. The first is sort of a essentially trivial observation that basically all known examples we have of hypercontractivity are in fact on good high-dimensional expanders. This includes things like the Hypercube, the Grossman, all these examples that I was talking about before. A second reason to believe it is that we sort of already know a weak version of this conjecture. It turns out that HDX already give a unifying theory for what's called spectral expansion. I don't want to go too much into sort of exact details of all these different types of expansion, but I think it's fair to say morally that you can think of this as sort of a weaker version of what we want to prove. It looks at only the second eigenvalue instead of all eigenvalues, but I think it's reasonable to think of it as sort of a weaker version of the conjecture we sort of already know is true. And the final reason is sort of a possible unifying tool set, something known as the local to global framework. It's actually how you prove this theory for spectral expansion. And it basically gives you some nice way to understand the interplay between local and global structure on these complexes, which naively seems to be sort of what's going on with these local non-expanding sets versus sort of global expanding pseudorandom sets. So naively, there's some hope of a unifying tool set to use here. And okay, so what do we actually prove in this work, and what I'll be focusing on the rest of the talk is basically the first steps towards this general theory. In particular, we prove the following statement that pseudorandom functions on high-dimensional expanders are indeed hypercontracted, that they satisfy a essentially full-strength version of the Bonami lemma, and therefore also that sort of pseudorandom sets on corresponding random walks on these objects, like think about them as the analog of this T1/2 operator we were talking about before, satisfy the same type of expansion characterization, that pseudorandom sets expand near perfectly on these objects. Okay, why are we not done? I sort of told you in the last slide that HDX capture everything we know. So why are we not already done? Well, there are a number of caveats that come with this result. In particular, probably the most significant one is that we only prove it for a special subset of HDX that are simplicial. This essentially means they're the downward closure of some hypergraph, and in particular, does not capture sort of vector space structures like the Grossman that seem to be crucial for understanding the UGC. So this is still very much an open direction. And also we'll see that sort of the expansion guarantees that we require are fairly strong. We need something called two-sided local spectral expansion, and we need the quantitative expansion to be pretty good, which also rules out some interesting cases like the symmetric. I mean, it still, captures a lot of new structure, a lot of new interesting sparse instances that sort of weren't known before, but we certainly aren't, at the full unifying framework yet. But I guess I'll mention before moving on that I think that these caveats are not inherent. That I think we believe that the tool set is out there, just requires some more work. Okay, so let's go ahead and move on to some details. First of all, I should tell you what high-dimensional expander actually is. So let me first say the underlying objects that we consider are these pure simplicial complexes. These are basically just downward closed hypergraphs. So these are collections of sets sort of size 0, 1, 2, 3 up through k, where xk is a k uniform hypergraph, right? This is just a family of k sets of 1 through n, and xi is given by downward closure. So this is all of the I sets that are contained in some k set in xk. So here's sort of a typical drawing of one of these. This is the complete complex. So we have these 4 triangles, and x3 the highest level, and then x2, x1, and x0 are just given by downward closure. And we'll call an object like this, we'll call a pure simplicial complex a high-dimensional expander, basically if each local restriction, if each local part of the complex is an expander graph. Okay, so let me formalize this a little bit. What are these restrictions exactly? These in the literature are something called links. So every face in the complex, every I face, has a corresponding restriction or subcomplex called the link of that face, xs, which is basically given just by taking everything that includes s in the complex and then removing S. So this is just a natural notion of restriction, but it's a little bit easier to see pictorially. So let's look at the link of 1. So what do? We highlight everything that contains 1, we throw out everything else, and then we remove 1, right, to lower the dimension by 1 here. And so now we end up with this corresponding graph that is the link of 1, which in this case is isomorphic to K3. It's not too hard to see. And so in this case, since when you generalize this, you get that sort of the links of the complete hypergraph are complete graphs. And so intuitively, it's not too hard to see that this would be like a great high dimensional expander, because complete graphs are very good expanders. So a little bit more formally, we consider a definition called local spectral expansion, or two-sided local spectral expansion. And basically, we say a complex X is a two-sided local spectral expander, gamma HDX. If basically the graph underlying every non-trivial link is what's called a gamma spectral expander. Again, I'm not going to go too much into the definitions. I encourage you just to think of this as sort of a complex is a high dimensional expander if every local part is expanding in some sort of common sense. Okay. So we want to talk about hypercontractivity and small set expansion on these objects, but to even define the Bonomi lemma, right, this was based on sort of this Fourier decomposition of F. It was based on saying that the Lodery parts of F are nice. So first I have to sort of tell you, what does that mean on an HDX? That's not clearly well defined. And so to do this, we introduce a new Fourier basis on HDX. We prove that sort of if you have a function on K sets of an HDX, then there's an explicit closed form decomposition, again into levels, just like on the hypercube of F0 through Fk, corresponding to sort of the degree I contributions, that satisfy the 3 following nice properties. These Fi, Fj are approximately orthogonal. They approximately satisfy something called Parseval's inequality, or equality, I guess here, which is basically just that you can move between the 2 norm of F and the 2 norm of the decomposition. And furthermore, that these F actually give an approximate eigenbasis of corresponding random walks, right? So this was the same thing we needed to use to move from Bonomi to small set expansion on the hypercube for any sort of associated random walk M. Again, think of this as just sort of the analog of the noise operator, this T1/2 thing. There exists some, approximate eigenvalue lambda I such that Fi is almost an eigenvector. And so these are basically exactly the properties you need to move from Bonomi to small set expansion. So, given this, we can sort of just focus on proving Bonomi lemma. So let me briefly, before going into that, briefly note some relations with prior decompositions. The exact form of this decomposition turns out to basically just be the natural generalization of Efron-Stein to complexes. It turns out it's actually the explicit form of a basis that was already studied in some kind of recursive notion on the complete hypergraph when in the original work proving sort of hypercontractivity in that special case. And I'll note that there are actually a number of known Fourier decompositions on HDX before, but they're sort of linear algebraic in nature and sort of very inherently only really work well with analyzing L2 structure. And so when you want to understand small set expansion and hypercontractivity, we need access to sort of higher norms. And this is why sort of this explicit Efron-Stein style decomposition ends up being much more helpful. Okay, it's worth noting that if all you care about is sort of L2 structure, all of these Fourier bases, including this one, we prove are essentially the same. Up to some O of gamma, term, these bases are all very close in L2. Okay, so naively, we might, now that we have this Fourier basis, we might hope to prove that it's hypercontractive, like on the hypercube. But you basically run into the same obstruction as on the p-biased cube. In this case, instead of sort of dictators or subcubes, the natural object is links. In fact, this is like the general, the natural analog of subcubes. So in this case, for instance, instead of the dictator on coordinate 1, we'll consider the family of all k-sets that contain a vertex 1. Again, you can show this as some very small density set fairly easily. But if you resample every vertex with probability 1/2, right, this analog of the 1/2 noisy operator, then the expansion is again about 1/2, right? Because you only leave the set if you resample 1, and that happens with probability 1/2. So again, sort of full strength Bonomi would predict that the expansion of this set is really good because it's a small set. But again, you seem to have this local obstruction where it's actually only 1/2. And so, okay, with this in mind, sort of what all these extended regimes did was prove that this was the only obstruction, right? So to formalize this a little bit, we'll call a function pseudo-random if it's not concentrated inside any link, inside any one of these local structures. So we'll say it's epsilon pseudo-random at level I. If across all links, I links, the density of F is at most epsilon. And we prove indeed that pseudo-random functions are hypercontractive on HDX. Right? In particular, if you have a function on k-sets of an HDX that is epsilon pseudo-random at level I, then some analog variant of the Bonomi lemma indeed holds. Okay, this is some complicated formula. The exact version is not too important. I'd encourage you to just think of this as for sort of sufficiently pseudorandom functions. The Bonomi lemma holds basically in full strength. And as a corollary, we immediately get that on sort of associated random walks on HDX, again, this is like the analog of noisy hypercube graphs or the hypercube graph, for instance, we get that pseudorandom sets expand near perfectly, right? So any subset S of K-sets, if it's sort of sufficiently pseudorandom, I've picked parameters here to be kind of simple, you get that the expansion of this set is like, approaching 1, is 1 minus epsilon to the O of 1, epsilon to the 1/3 or something like that. And typically sort of it's the contrapositive of this that's useful. But this basically tells you is that if I give you a non-expanding set, then you're always going to be able to find some low-level link of constant density, where even though the overall function is sparse, you'll be able to find some link with like a booster, something that's much denser than expected. And this can kind of be thought of as a tight analog of these KKL type or Bourgain type theorems in the sparse regime, where your function is sparse, that basically non-expanding sets can be characterized as those that are very dense within some local restriction. Okay, so I have a couple minutes to talk about the proof of this. I really want to focus on sort of one key lemma that really ties everything together. Okay, so first, sort of old methods of proving hypercontractivity typically rely very strongly on product structure or on some sort of strong self-symmetry, like on the symmetric group. And inherently, this is sort of a problem for HDX, because HDX can be very far from products, right? They can be sparse, they can have high correlations and dependencies, they can be very asymmetric. So naively, it doesn't seem like you could apply these previous tools. And so maybe to be a little bit more concrete on sort of why these are far from products, let's consider a bounded degree HDX, which means you have n vertices, but each vertex maybe only appears in a constant number of k-sets, like 10 k-sets or something like that. And so each vertex might have sort of measure 1 over n, but as soon as we condition on another vertex, well, either this only appears in like 10 things, right? So either the probability of x1 condition on this is like a 10th, or it's 0. It doesn't show up at all, right? So we jump from like 1 over n to a 10th or to 0. We have these massive shifts in probability, whereas on a product, if you condition on one thing, sort of the point is that things are independent, right? So conditioning shouldn't have this sort of massive shift in effect of an individual variable. So naively, this seems like a problem, but it turns out that the key idea is that while sort of at the level of individual variables, HDX are very far from products, it turns out that in some sense, on average, they actually do act very much like products. They essentially are independent on average. Okay, so what do I mean by this? Well, slightly informally, let's say that we have some I face tau, and we're considering sort of the conditional distribution on tau. What we prove is that for any function f, the global and conditional expectations of this function, right? Sort of the expectation of f conditioned on tau versus it's just global expectation over the HDX, that their difference is controlled by something with small spectral norm, is controlled by some operator with small spectral norm. And what this means morally is you should really think about this as saying that when we're analyzing sort of outer expectations, something like a fourth moment, we can treat HDX like they're products. We can basically replace these conditional expectations just as if sort of the conditioning didn't happen, as if the conditioning didn't have any effect. Because when we're analyzing expectations, you can then use sort of analytic techniques to ignore these, these gammas end up contributing some small O of gamma error term. And so you can basically just pretend that you're on a product, even though you're maybe on this sort of very sparse different structure. And that's really sort of the key to getting these new hypercontractivity theorems on these more general sets of objects. Okay, I want to very quickly sort of go for the proof. Since it's very simple, at least in the case for sort of the special I equals 1, j equals 1 case. The proof here is really you just expand out this expectation into these two sums, and you observe that sort of this first sum is really just sort of the transition probability or the applying the underlying random walk on sort of your graph. So this initial sum is basically just applying the underlying walk on a link to f. And the second sum is just the stationary measure, right? This is just applying the stationary measure to f. And so their difference is just the underlying random walk of the graph minus the stationary measure. And this is exactly one way to characterize the spectral expansion. So in particular, the spectral norm of the adjacency matrix minus its stationary operator is exactly the two-sided spectral expansion of the underlying graph. And therefore, this lemma, at least for the I=1 case, is actually exactly equivalent to two-sided local spectral expansion. This is just an equivalent way to view high-dimensional expansion, that on average, these objects are like products. Okay, I'm basically out of time, so I'll end just mentioning, I basically mentioned some of these open problems before. It's sort of still wide open to understand hypercontractivity and these small set expansion behavior beyond sort of the simplicial case in cases like the Grossman that seem to be so important for hardness approximation and unique games. And also there are sort of a number of weaker types of high dimensional expanders, like one-sided local spectral expanders, or complexes with sort of quantitatively weaker expansion, like the symmetric group, where our arguments sort of break down, but it seems quite plausible that you might be able to prove a more general characterization for these objects. Okay, thanks so much.